Well, that word, we talked about poly, the prefix meaning many. So far, we've dealt with only monoprotic acids. Mono, of course, means one. What that looks like is, and we've done these before, whether it's a strong acid or a weak acid, if it's a monoprotic acid, it dissociates in just one step. The hydrogen breaks apart from the anion. That's what the A represents. The anion has a -1 charge, which is why there's only one hydrogen there to balance it out. Okay, we've been dealing with all of those. And you go through and you can set up the ice table for it, figure out the concentration of hydrogen, and figure out the pH. Diprotic, how many hydrogens do you think diprotic has? Two. Okay, so that would be H2A. What would be an example, a real life example? Yes, H2SO4, sulfuric acid, H2CO3, carbonic acid, H2SO3, sulfurous acid. These are all examples of diprotic. They can either be strong or weak. The only strong one here is which one? SO4, okay? All you need to know about this is that diprotic acids dissociate in multiple steps. So the first thing that's going to happen is that one hydrogen is going to dissociate away from that, and you're going to be left with HA. That HA is going to have a negative charge. So that's step one. Then the second step is that the HA dissociates into the other hydrogen and the anion with its -2 charge. That's step two. So it doesn't just like have both hydrogens come apart all at once. Just one hydrogen comes off first, and then the dissociation continues. Triprotic, 3 hydrogens. Real life example? Yes, H3PO4, phosphoric acid. Yeah?
For the diprotic and triprotic, is it only the strong ones, or is
No,
it all?
it's all. So it's just the category for all, either strong or weak. Okay? This dissociates into in three different steps. First one hydrogen comes off. We're left with H2A with a negative charge. That's step one. H2A dissociates. One more hydrogen comes off. We're left with HA, 2 minus. Because now it's lost 2 hydrogens, so it has a -2 charge. And then the last step is that the HA, 2 minus, dissociates into the last hydrogen, and then the anion, which has a -3 charge. So there's 3 steps for the dissociation of triprotic acid. And yes, this is for either strong or weak. If it's strong, then it'll fully dissociate, and if not, then just a small amount. The only other thing you need to know about these polyprotic acids, is that if it dissociates in multiple steps, there are Ka values for each step separately. There's a chart in your book on page 651 that shows these different common polyprotic acids and the different Ka values. So you'll see for phosphoric acid having 3 steps, this is the Ka value. It's the dissociation constant for the first step of dissociation, when the first hydrogen comes away from the phosphoric acid. And that number is always much bigger than the Ka2, which is the dissociation constant of the second hydrogen. And so you're going to have a much smaller percentage of dissociation for the second one, and even a smaller dissociation for the third one. And so the numbers just get smaller the more steps you have in the dissociation. Okay, so that's it. You need to know those things about polyprotic acids. Now remember, in chapter 14, the question is always pretty much, what is the pH? Okay, that's not changing here. In section 14.8, the question is still, what is the pH? But instead of dealing with things that are obviously acids, like they have, the hydrogen ion, or obviously bases, like NH3 or some hydroxides, we're dealing with salts. Now, salts are any kind of ionic compound that ionize in water. They just dissociate, they break apart. And depending on what ions they break apart into is going to determine if the solution is acidic, basic, or neutral. So you have to know how to look at the different ions separately to figure out what it's going to be. So like, for example, this one. We're going to talk about this one a lot. This is sodium acetate. Okay, it's just a salt, right? I've got a sodium ion, I've got an acetate ion. They break apart when it dissolves in water. Somehow, it's going to affect the pH of the solution, and we need to figure out how it does. So we'll start first by talking about salts that produce neutral solutions. And then we'll talk about acidic solutions and basic solutions. When you're looking at salts, you're going to look at the ions separately. So if we're talking about sodium chloride, you want to think about sodium ions, chloride ions, because when they're in water, it doesn't stay together as NaCl. It separates, it ionizes. For sodium nitrate, sodium ions, nitrate ions, here we have potassium and chloride ions. So the general rule is that if you have a salt that has a cation of a strong base, what that means is like Na, I know that Na could be the cation of sodium hydroxide. Sodium hydroxide is a strong base. Potassium, so you want to think about basically if it's a base and it's attached to hydroxide, would it be strong or would it be weak? Potassium hydroxide is a strong base. And so cations of strong bases have no effect on the pH whatsoever. So as you're going through and you're looking at all these salts, I kind of cross out the ions that don't affect the pH at all, so I know what else I'm working with. So again, this sodium goes with sodium hydroxide, so it crosses out. Anions of strong acids do not affect the pH of a solution at all. So Cl is the anion of hydrochloric acid. This nitrate is the anion of HNO3, which is nitric acid, which is strong. So that doesn't affect the pH at all either. None of these ions that are here affect the pH of the overall solution. So in water, those solutions would be neutral. Okay, so you're looking for cations of strong bases or anions of strong acids. And if they're there, then they don't affect the pH. But what if they do affect the pH? How do we know? And how do we figure out what the pH is? So, next one, salts that produce basic solutions.
Would an exception be like a diprotic acid?
Diprotic?
Yes.
Um,
I don't know in English. Since it'd be creating.
No. No, it would still be fine. Like if you had SO4 sulfate, that would be the anion of a strong acid, so it still wouldn't affect the pH of the solution. So it doesn't matter how many hydrogens or anything there are. All right, sodium acetate, when it dissolves in water, ionizes into sodium ions, acetate ions, and then water is a major species, of course. I've got all three of those things included in the solution. We talked about in the previous section that sodium ions do not affect the pH of a solution at all because it is a cation of a strong base, so it doesn't affect it. So all that I'm really paying attention to here is the acetate ions in the water and what's happening. If you have acetate ions, C2H3O2, in water, that's liquid, this is aqueous, then we're going to have some hydrogen moving around here. So one of the hydrogens is going to come off of the water and hook onto the acetate ion to give me acetic acid molecules. What's left over after the hydrogen leaves the water here? OH. Okay, these are all aqueous here. Now what I have is, I've got acetic acid over here, but I have hydroxide ions over here. Hydroxide ions are very strong, and we always know that strong stuff wins over the weak stuff. And so the fact that I have hydroxide ions being formed means that this is going to be a basic solution. And so this ion by itself is basic because it produces, well, hydroxide ions are produced in water. And those hydroxide ions make the pH basic. Now, this counts as my base, my acetate ion. The acetic acid over here is the conjugate acid, but it's super weak compared to the hydroxide. Later on, you're going to use this to write out the Kb expression. So, since it's basic, I write the Kb expression, which would be, products over reactants. So my HC2H3O2 multiplied by my concentration of hydroxide ions over my concentration of acetate ions. Water's not in it because it's a liquid. Now, the only tricky thing here is that in your book you have a list of Kb values. Okay, what I wrote here is the Kb expression for the acetate ion. But if I look at my Kb table, is the acetate ion on here anywhere? No, there is no Kb value for conjugate bases, which is basically what this is. It's the conjugate base of acetic acid. So I don't know that. I need to figure that out. I do know the Ka value for acetic acid is 1.8 times 10 to the negative 5. That's something you can look up. So then the question is, how do you figure out the Kb value for its conjugate base, which is the acetate ion? And so here is that very important relationship between Ka and Kb of conjugate acid-base pairs, and how we can figure that out. Now, it just, in the notes, I happen to type out for any weak acid and its conjugate base, but it's the reverse is true. If you have the weak base and its conjugate acid, which is what I have up here, weak base, conjugate acid, those two K values multiplied together equals Kw. Kw is 1.0 times 10 to the what number? Negative 14. Okay, so if I know the Ka value of my conjugate acid to be 1.8 times 10 to the negative 5, and I know Kw, I can figure out Kb for the acetate ion. So we can go through and use that to solve for X and calculate pH and all of those things. So one more just like quick example, and then I'll do a calculation problem. NH4Cl, ammonium chloride. Chloride ions do not affect the pH. Why? It's the anion of a strong acid, hydrochloric acid. I'm left with NH4. Now, NH4, anything really, if it's positively charged and it's not one of those ones you can cross out, then it's going to make the solution acidic. And why? Because if I put it in water, since it's positively charged, it has an extra hydrogen to get rid of. So that extra hydrogen is going to come over here and make H3O, hydronium ion, which makes something acidic. It also makes NH3, which is a weak base, but the hydronium ion kind of wins in this situation and makes the solution acidic. So NH4 ions in water make acidic solutions. Any positive ion that you can't cross out makes acidic solutions. Okay, so let's go through and do an actual pH calculation using that. Then I'll have one more thing and I'll be good. Are you not done? A lot of stuff in this problem is exactly the same as what you've done before. There's just one added little piece of calculation or information that you need to work with in order to get the final pH. The question is still, what is the pH? And they give you the initial concentration, 0.14 molar of sodium acetate. do sodium ions affect the pH? No, they do not. Okay, so acetate ions is all I'm left with. And again, if you're left with the negative ion, it's going to make a basic solution. So I need to calculate the pH of this. And you need to write out the reaction because you're going to need to set up an ice table. Because if the question is asking me for the pH, then I have to figure out the concentration of either hydrogen or hydroxide ions that I have so that I can negative log it and find pH or POH. So you always have to write out what's going on. I end up with HC2H3O2. We wrote this out already. Hydroxide ions. My initial concentration over here is 0.140. I don't care about water. 0, 0. And I should be better about this. These are aqueous, all of them, which is why they're included in the equilibrium expression. Plus X, X, plus X, X at equilibrium minus X, so 0.140 minus X. I want to solve for the pH. So I know if I get the hydroxide ion concentration, I can solve for the POH and subtract it from 14 and get the pH. So I can go ahead and set up an equilibrium expression based on the acetate ion. So it's a base, so I have to set it equal to Kb. Kb is equal to x squared over 0.140 minus x. Now here's where that previous equation is important. I don't know the Kb for the acetate ion, but I do know the Ka for acetic acid. And since they're conjugate acid-base pairs, and I know that Kw equals Ka times Kb, I want to solve for Kb. Kb equals Kw over Ka. And again, that Ka value is one that you can look up in your chart for acetic acid. So it's 1 times 10 to the negative 14 divided by the Ka value when you look it up for acetic acid is 1.8 times 10 to the negative 5. That gives me a Kb value of 5.56 times 10 to the negative 10. I can take that number and plug it in over here for Kb. And then you can solve for x once you know what the Kb value is. And x is equal to your hydroxide ion concentration. So make sure you're looking at your reaction and what you're solving for up here. Hydroxide ion concentration 8.77 times 10 to the negative 16 molar. And I'm not going to go through all of this again, because you know once you have hydroxide ion concentration, you negative log it, gives you POH is 5.06. pH equals 8.94. The only extra step here is that you have to solve for the Kb of the conjugate base, because that's not just something you can look up. So that's the extra added step. Everything else is the same. Ice table, negative log it once you get X and your concentrations. Okay. This is zero. This is 0.
Right. So you just,
Well, I just put
it
it in
can't be
myself.
smaller than what Kb is initially. You're square rooting it. Kb is to the negative 10.
Maybe I wrote the wrong one. Maybe it's 10 to the negative 6. I just wrote it wrong. Okay, so I'll recheck that calculation. But go ahead and start writing this down. If both ions affect the pH, NH4, acetate ions, none of them are ones that you can cross off, then you want to figure out which one wins, basically, to make the solution either acidic or basic. Oh, I just wrote it's times 10 to the negative 6. Where's your answer?
Right. There's no scientific notation.
Oh, yeah,
it's the
so
same
it's
thing.
9 times, yeah.
Yeah.
This is not 16, this is a 6. I don't know what I... You're right. I thought you said you got 9,000, and I'm like, I know
No.
that's not right. There you go. In ammonium acetate, none of those ions come from either strong bases or strong acids. So none of them cross out as far as not affecting the pH of the solution. They both are going to affect the pH of the solution. So how do you figure out which one affects it more is the question. And I don't think there's any like actual calculations you have to do here. You just have to recognize if the solution is going to be acidic or basic. So what you want to do is you want to look at each ion separately, and for the acidic one, look up the Ka value. So for NH4, oh wait a second, wrong chart. There's a chart that has your Ka values, and NH4 is actually on there. Here we go. NH4 has a Ka value of 5.6 times 10 to the negative 10. For acetate, I can't look that up on any chart. Okay, I want to know what the Kb value is. So for the positive end, you want to figure out what the Ka value is. For the negative end, you want to figure out what the Kb value is. If you can't look it up on the chart, you need to solve it. So Kb equals Kw over Ka. I did this in the previous problem. Ka is the constant of the, whatever its conjugate acid would be. So that's of acetic acid. Okay, so that is actually 5.6 times 10 to the negative 10. These numbers are the same. Since Ka equals Kb, then they basically cancel each other out, and the overall solution is neutral. If you went through and you figured out the Ka value for the positive end, and it was bigger than the Kb value of the negative end, then the Ka wins and the solution is acidic. If your calculated Kab value is bigger, then the basic part of it wins, and so the solution is basic. Okay? Those problems are due on Friday. Some calculations, a lot of identifying if solutions are going to be acidic or basic.